Welcome back in our channel. Today we have two applications about first ODE linear differential equation. The first application is Newton's law of cooling, which is also applicable for heating too. Here the rate of change of temperature with respect to time proportional to the difference between the temperature of the body and the ambient or the surrounding. And we just remove the proportion sign and put a constant, which is K, and it depends on the surface area of the body and the material itself. And we got this equation, and here we P of t equal K and Q of t equal KT as in the temperature of the surrounding. This is constant, and this is constant too. First we find the integrating factor. As you remember from the last videos, we found out how to find it. And here the integrating factor equal E to the power KT. And this is the solution of the equation. 1 over I of t times the integral of I of t times Q of t plus C. See, this is the constant. There's a difference between this C and this K. This K is related to the material itself. So the surface area or the material type, what type of material, but this is, we got it from our solution, the constant of integration. So the example, a body with a known temperature is placed in a room with the temperature of the room is 30 degree Fahrenheit. After 10 minutes, T became 0. And after 20 minutes, T became 15. Find the initial temperature of the body. The solution. We use this equation here. We put our integrating factor, it's just a few steps. And we found out this is the temperature. This is the final relation of the temperature equal Ts, which is T of Tr, the same, T, the room, the surrounding, the ambient, whatever, plus C e to the power minus Kt. And here, this is our final relation. So at T equal 10, after 10 minutes, the temperature here, we put T equals 0, and the temperature of the room is 30 plus C E minus T here, 10 and K. We need to find C and K, both unknowns. At T equal 20, the temperature is 15, the same, 30 plus C, E, here we put 20, at time 20 minutes. And then we got two equations. We solve them, just algebra, 2 or 3 steps. We divide one on the other, and we take ln for both sides. We found out C equal minus 60, so T equal minus 60 E. This is our relation. This is our solution. The temperature at any time, you just plug the time here, you will get the temperature. And so here we found C and K equal 0.069 and C minus 60. And then we applied So here is this is the final relation. The temperature of the body at any time t. We just plug the time and we get the temperature of the body. The second example is Newton's second law of motion. Summation of force equal ma. Means the acceleration of the body depends directly upon the net forces applied on that body and inversely to the mass of the body. And here is the summation of course, here we have F is vector. And the A is vector too, because it has magnitude and direction. The mass, no, just magnitude. So here the weight minus mg, which is g, the 32 feet per second square, the acceleration, minus kv equal m dv over dt. This is the acceleration, derivative of the velocity. And then again, this is linear differential equations. P of t is k over m, and q of t is minus g. And we find here's the body, just the body is rising up, so our positive direction will be this direction, and this is the ground. We have two forces affecting the body. The air resistance, the driving force, kV, and mg is the weight of the body. Both acting against the body. So both they are down and the body is going up. So this is the solution of our differential equation, 1 over I of t times integral of I of t times q of t plus c. This is c constant of integration. This is different constant related to the drag force or the air resistance. So the integrating factor here we find it's e to the power k over mt. Just normal solution as we did before, and then this is we plug the integrating factor in this solution. We got v equal minus m over k plus c e to the minus k over mt. This is equation 1. Our initial condition, to find the c, we need to apply our initial condition. We use our initial condition, which is at t equals 0, the velocity of the body was 0. So we plug this in the solution. We put v equal v naught, and then we found out c equal v naught plus mg over k. Therefore, the velocity of the body at any time is v equal this equation. So this is the equation of finding the velocity at any time. Whatever the v naught, the initial velocity, just we put it here, and we know the mass of the body, the g, it is known, also k, it is constant, and so the only thing, and we put t any time, so we find the velocity from here to here at any time t. The body reaches its maximum height when v equals 0, because as you know, the body will have the acceleration up at the end. The body reaches the maximum height at v equals 0. When the body stops, it will come back again. So when v equals 0, and then we plug it 0 in the equation here, we got this. And we find from our, just few steps of solutions, we find t equal minus m over k ln mg over v node k plus mg. We just take the minus sign to the ln, to the other side, we put it here, and then so we just few steps of solution, and we find this is our the value of the t, the time, which is give us the velocity at any time. Thank you for watching my video, and see you in the next videos.